Hi everyone, this video is going to cover a basic addition problem from section 6.3, which deals with adding and subtracting rational expressions. Before we actually get into the full-blown example, I want to give you some background history as to why we add and subtract only with a common denominator between those two rational expressions. Basically, let's start off really basic and then we will start off with a little bit more. So say I give you, a penny. And then I also give you a nickel. If I ask you how many cents you have, if you were to do this incorrectly, you would say, I have 2 cents. In other words, you're just counting how many coins you have in your pocket. We, of course, know that this is not correct because each coin has a different value attached to it. So in order for me to actually find out how many cents we would have to do, I could actually break this up into 5 individual pennies, for example, in order to see that I have equal weighting now. Okay, this kind of goes further. Okay, so let's start off with a basic example. Say I have 1/2 plus 2/5. Again, what you want to note here is that the denominator of 2 carries a different value or weight than the value of 5 in the other denominator. Okay, so to kind of show you this graphically, a 1/2 would kind of be represented by this whole value if I were to cut it in half and only be concerned with this shaded red piece. Okay. Very similarly, if we were to look at 2/5, we would go ahead and try to cut this into 5 equal pieces, and the 2/5 would be represented by the 2 pieces that I have shaded in blue. So notice that each piece is not the same size, and this is why we actually have to find a common denominator here in order to find things that are the exact same size. So that's why I'm going to come through here with a purple. That's why we would say, for example, we know that the common denominator between 2 and 5 is 10. So essentially what you're doing when you find a common denominator of 10, so note here that if I take 1/2 and rewrite it with a denominator of 10, this becomes 5/10. And then if I take 2/5 and rewrite it with a denominator of 10, this becomes 4/10. Okay, so in other words, I'm going to cut this so that this value has 10 pieces in it. Notice that when I did that, those 2 shaded pieces in blue have now become 4 shaded pieces. And then when I come through here and cut this into 10 pieces of relatively equal size, notice that the red pieces, I have 5 of them. Okay, so the reason why I find a common denominator is essentially I'm cutting these whole values, in other words, these circles in this case, into equally sized pieces, so I can count the equally sized pieces. Very similar to taking a nickel and breaking it into 5 pennies in order to add it to the other penny that I have. So that's why we actually find a common denominator when we add or subtract. We want to make sure that when we count these pieces that they are of equal size. So again, just to kind of drive this home, if I give you something like 2 plus 3, this is really saying that I have 2 whole pieces over here, so they are the same size, and I'm going to add it to the 3 whole values over here. So I have a total of 5 whole pieces. Okay, so hopefully I have driven that home, and now we're ready for a full-blown example with rational expressions. Get excited, everyone. Are you excited? Can you not wait? Are you on the edge of your seat? Are you fast-forwarding right now? I understand if you are. So let's go ahead and we'll take a look at the following. I'm going to take 3 over 4ab squared minus 5 over 2a squared b. So what I'm going to go ahead and do now is I need to find a common denominator. So I'm going to focus all of my attention on just the denominators. So first off, I'm going to take 4ab squared, and I'm just going to break it up. I'm going to put it into its prime factors. In other words, I'm going to break it into the prime values, values that I cannot break down any further, that would multiply together to give me 4ab squared. So for 4, its prime factors would be 2 times 2. 2 is a prime number. I can't break it down any further. A is just there, and then b squared would be in expanded form, b times b. So then, if I move over to 2a squared b, again, 2 is a prime number. A squared is written out as a times a, and then there's only one b. So, as we had mentioned in class, we want to basically make sure that the denominators are identical. So, we already know that both of them share a 2, both of them share an a, and both of them share a b. So really what I need to do then is kind of take a look and say, all right, the 4ab squared, it needs an a. So I'm going to multiply, and I'm going to go ahead and write it down here so I have a fresh view and I'm not kind of cramming all my information in there. I'm going to multiply the top and the bottom by an a. So now I'm going to kind of check to see what 4ab squared has that the denominator of 2a squared b does not have. And I want to note here that it does not have a 2 and it does not have a b. So that means I'm going to multiply the numerator by a 2b and the denominator by a 2b. So let's go ahead and clean this up. So 3 times a gives me 3a all over 4 times a times b squared. So this can be kind of summarized to be 4a squared b squared. Then we have our minus sign. 5 times 2b gives you 10b. 2 times a squared times b times 2 times b. 2 times 2 is 4, a squared, b times b is b squared. Oh, happy day, everyone. We have common denominators. So I'm going to go ahead and just write this as 3a minus 10b all over that common denominator of a squared, b squared. And I'm circling this because this is as far as I can go. If you notice, taking a look at the numerator, 3a minus 10b, there is nothing in common there. 3 and 10 have no common factors. A and b are completely different variables, so you cannot factor anything out there. As a result, there's nothing that you can cancel out within the denominator. Because again, remember, this 3a minus 10b is one value. It is two terms connected by a subtraction. So remember that we can only cancel out factors and not terms. So since we have a subtraction on top and a multiplication on bottom, that automatically prevents, and we can't factor anything out of that subtraction, that tells us to stop. This is where we are done. Okay? There will be another video coming up talking about a more complex problem where you would have to do more factoring in the denominator.